And like I said, I think this is really, at the moment, probably the most exciting part of mlr3, yeah? Because you can do so much interesting stuff with it. And mlr3 pipelines is, well, about constructing machine learning pipelines or machine learning workflows, okay? Complex machine learning pipelines, complex. So it's kind of a modeling language for machine learning workflows. And we all know nowadays that this is pretty important, that machine learning now, applied machine learning, is about a lot more than simply taking a kind of completed, already externally pre-processed data set and running a single algorithm on it, maybe tuning it a bit, evaluating it, and then you're done, right? The most important steps of applied machine learning nowadays often happen in feature extraction, feature pre-processing, feature selection. Data is quite dirty, yeah, nowadays. You have to kind of do a lot with it before you go into your ML algorithm, especially if you want to achieve optimal or good results. And yeah, mlr3 pipelines is kind of a design language in order to allow that to you. And if you want to kind of squeeze out the last epsilon of performance, if you look at Kaggle, how people usually win competitions, they often use a second ingredient, and that's about ensembling, so model averaging, model stacking, and so on. And also, this is also possible with mlr3 pipelines, but mlr3 pipelines actually allows you to do a lot of very complicated things because it's a quite abstract and very general type of, well, workflow language geared towards machine learning. So my kind of running example for the beginning is just simple linear pipelines where we, for example, do something like scaling of features. Then we encode factor variables because our ML algorithm can only handle doubles. Then we do maybe some imputation to handle missing values, and then we go into the learner. And this is what I would call a linear pipeline. And this is what many people are now, well, I guess are pretty happy with, but mlr3 pipelines can do a lot more. It can actually work on graphs. So how do workflows look like from an abstract point of view? So we basically have two building blocks. So we have like a computation that's being computed on something. And this is what we call a pipe operator. And this is what you see here as the nodes in the graph. So each of these little nodes here, these pipe operators, takes one or multiple input objects. It computes one operation on them. And then, well, it gives out the results, which is usually of one object, but it can also be multiple. And you can also see the structure here, like the connections, these edges that specify in what sequence stuff is happening, how these computational steps are interconnected, that control how information flows. And if you, well, combine nodes and edges, well, what you get is a graph. In this case, kind of a computational graph, right? And that graph we call a pipeline. I guess we could have also called it mlr3 graphs, but pipelines is the more popular term. Or I guess we could also call pipelines kind of a data flow modeling or data flow programming language, because usually on these, not always, but most of the time, what flows on these edges here is some form of pre-processed data. So let's now start with the pipe operators. How do they work? And pipe operators, in a certain sense, you can think of them as a generalization of an ML algorithm. So you've already understood how an ML algorithm works like, right? Like data goes in, and then there's a training procedure, and a model comes out. And then there's a predict procedure where also data goes in, and then a prediction comes out. Yeah? And pipe operators are kind of a generalization of that. So that they don't necessarily train models, but they do something on data. Well, in a certain sense, you could say they also learn something on data. And they are objects. So they have a constructor, again, with a nice little sugar. So you can use these PO, this PO function here. And you can construct your pipe operator. And in the beginning, I will use the scale operator as a very simple example, because I think most of you will understand how scaling works. And now, the important thing, and what makes everything a little bit more complicated, is that this operator, it's not a single function call, okay? So it's not just one function. It's unfortunately in machine learning, it's always two functions. So it's training and prediction. So what happens in training? So training data goes in. We scale the training data, so we scale each feature, and we transform it into scaled data. And while we are scaling the data, we also store the scaling factors. So usual scaling in statistics, I mean, there's different versions of it. One scaling is subtracting the mean and dividing by the standard deviation for each column. And this is what I call the scaling factors here. And this is what you could actually call also learned parameters. So in a certain sense, we are learning them on training data. And here we now store them as we store for a learner, we store the model inside of it. We now store these learned parameters. And during prediction, something slightly different happens. So test data comes along. It's again a blob of data table. We push it inside of the operator, but now we don't learn anything. We simply apply the learned scaling factors from training, and transform data again goes out. So every pipe operator always has a training function and a prediction function. Yeah. And there's actually more complicated operators that have multiple inputs and outputs. So I think this type of operator here we call a pre-processing operator. So for pre-processing, so that's kind of the abstract base class. So for pre-processing operator, always training data goes in, transformed data goes out during training, and during prediction, again, data goes in and data comes out. But we have more complex operators, and some of them are actually either take multiple inputs or produce multiple outputs. All of them I will show later in more complex examples, so I don't want to kind of explain them here prematurely. So let's see how this actually looks like in our code. So we construct our pipe operator for scaling, and now we train it. And operators, because they can take multiple inputs, they are always trained on lists. So also what I'm showing here is how the thing works as a single computational step. Later on, you really wouldn't do this by hand because you would connect them in a graph, okay, and in the pipeline, and just use that. Just showing this here, so you can understand how it works. So the training function always takes a list, because it can be multiple objects. In this case, it's just a simple list of a task. And now we train it, and now we can peek inside, and the output is also again a list, because it can be multiple objects. And here you can see that it's simply, the output is simply the transformed data. So you can see this is the iris task. I think most of you have seen this, and you can see some weird feature values in here for iris. And the reason that these look a bit non-standard is because I've subtracted the mean now and divided by the standard deviation. Also, each pipe operator has a so-called state, and the state contains exactly these guys here, so these learned parameters during training. So if you look at the state, you can see that I have a list, because we're using the scale function from R that I'm guessing most of you guys also have seen before. So that always computes this center list, or center vector, I should say, with the means of each feature and with the scalings here, so the standard deviations of each feature. And you can peek into this and look into this. So this is what we have learned during training. And during prediction, well, again, you use your pipe operator, you use your prediction function, again, you use a list, and up here I just created a smaller task. Some of the extra code here is just on there, so you can actually squeeze all of the output on the slides. So it's basically just PO predict from a list on the task, and you can see here how I'm now transforming this new data with the learned parameters. If you want to get a feeling for what's inside of mlr3 pipelines, I guess it's actually best not to look at my slides here, but to look at Martin's webpage and our book. But all pipe operators, again, are in a dictionary. You can list this, so they don't even fit on the slide anymore. There's a lot of stuff in there. So I guess I'm not going to read all of this out. So there's a lot of pre-processing stuff in there: scaling, box, Cox transformations, PCA, ICA, a lot of imputation techniques, a lot of feature selection techniques, especially filtering methods, categorical data encoding, so one-hot, treatment encoding, impact encoding, sampling methods, sampling for class balance corrections, ensemble methods, which you will see later on here, branching, which is also very complex meta type of thing, which allows alternative data flows. So there's some stuff already in, there's feature union in there, which we will also show you later for ensemble construction. There's text processing in there, date processing, and we have some planned stuff for spatial temporal data, some ordinal stuff, and some outlier detection that exists on GitHub in various stages of development, but not really in pipelines yet. Okay, so let's make it more interesting. Let's now connect these things into full graphs. So in order to connect stuff, the package gives you a couple of operators. So the most important operator is this pipe operator here. So we kind of created a new R operator, and that concatenates different pipe operators in a sequential manner, or it concatenates graphs. So what this basically does is, So in the most complex version, you have a partial graph here, and that graph has a right-hand side. So it has a couple of nodes which have outgoing edges which are not connected to anything. And then you have a partial graph here which has a left-hand side. And so some of these nodes have incoming edges which are not connected to anything. And these are now connected by this pipe operator. In the simplest case, you would just have something like this here. We just connect this guy to this to this, and then this to this, okay? But it also works on more complex partial graphs. And this is obviously important, right? So you can build more complex stuff from simpler elements. And then there's the G-union operator. The G-union operator is something that's not, it's even simpler. So it takes two partial graphs and it creates a new graph out of them by not connecting anything. And then there's a little helper function that's quite useful, for example, in ensembling. So that's called the pipeline or G-replicate function. And that creates copies of graphs or partial graphs, and then simply merges them together, calls the union operator on them. So you have like 10 different copies of the same element in your graph, which is pretty helpful, as you will later see in examples. So let's now have a look at, and of course, obviously, I should also mention how you can get machine learning algorithms from mlr3 into pipelines. Well, there's just an operator which is called the pipe op learner, and you can put any mlr3 learning algorithm inside of it, and then you get this little pipe operator here which applies this machine learning algorithm, this mlr3 learner. What you can also do is you can wrap each pipeline as a graph learner. So that's basically just a little piece of connecting code. You'll see this in the examples very quickly. So this kind of creates from a pipeline a learning algorithm this makes the learning algorithm out of this complete pipeline and allows you to use everything from mlr3 again on this, including resampling, benchmarking, tuning, nested resampling, so everything that we've shown to you before. So how does this now work with linear pipelines? Super simple. Write down pipe operator scale, write a pipe operator for encoding, and always connect them with this pipe operator here, with this pipe thing. Then something for imputation. Maybe we impute all NAs with the medium of the column, and then we use a decision tree. This thing here creates a linear pipeline. We're basically done. You can now wrap this in a graph learner, and after you have done this, you can now use resample on this, you can use tune on this, you can use benchmark on it. Done. You are now basically in the world, well, in Michel's world, so to speak, in mlr3. And of course, I can train it. And if I train this, for example, just to make this clear, what happens is training data is pushed inside of this. We learn the parameters here, we learn factor levels here, we learn feature medians here, and of course, we learn our decision tree in the last step. And in prediction, new data goes in, we scale it with the learned factors. With the scaling factors, we do the same encoding for factors, we impute data as we've learned it, and then we apply the decision tree. Some extra comments on how to practically work with this. So obviously, you can set hyperparameters of all of these pipe operators. This is a lengthy piece of code, but it's not very difficult to explain. So every graph, every mlr3 pipeline objects contains a list of pipe operators, and this list is named. So all of these pipe operators have IDs. So they have standard IDs. The scaling operator is called scale, but you can rename it. You can call it foo, okay? And then you can access this list here with the ID of the operator. It has a param set, and as for learning algorithms, you can access values and set them. So you can read them out and you can set them. It works exactly in the same manner as for mlr3 learning algorithms. So access this list here with the ID and then simply work with the param set. If you can do that, if you can select from a graph each individual pipe operator, you can obviously access the state, as I've shown to you before. And you can read out the state of each pipe operator after the pipeline has been trained. And if you set a little debug option, you don't do this by default because it would waste memory, you can also access the result of the pipe operator. So if you do the computation here, so if data, for example, is pushed through the thing, right? So I guess for example, in training, if data is pushed through this thing, it gets transformed, and maybe you want to see how the data actually looks like, how the object looks like, especially if you want to debug a complex pipeline. That makes sense. So set this debug option, and then look at dot result, and that gives you the output. So what actually is, well, which is computed for this step, which is computed here, and then flows into this guy. And we can create nonlinear pipelines, which is, I think, the most exciting thing. So some people already asked in the Slido, can I do ensembles with mlr3? Answer is yes. It's actually on this page here, how you can, for example, do your own bagging method. So here I'm creating a pipe operator with subsampling. So I'm randomly selecting, like, for example, 80% of my rows of my training data, and then I'm running a decision tree. Now I replicate this 3 times and then use the pipe operator for averaging. So this would create a graph that looks like this. So I take this guy here, replicate it 3 times, and then do majority voting at the end. It's my own bagged tree, so that's nearly a random forest, right, that I created with 2 lines of code. And if you train this, it looks like this. Or you can do stacking. So here I'm already doing something pretty complicated. I'm taking a linear model, I'm taking a support vector machine, and I'm using the null operator. I'll explain this in a few seconds. So, and I'm not only creating a pipe operator for the learner, I'm actually creating a pipe operator for cross-validating the learner. So each time I push data in here, the thing gets cross-validated. So some of you guys already know stacking better, and you know that you should actually use cross-validation, in stacking. If you later on create your ensemble on the predictions, so this cross-validates this and pushes out the cross-validated predictions. The same here, and this null operator actually just passes data along. So this actually passes along original feature values. Then I do a feature union so that C binds the predictions of this guy, the predictions of this guy with the original features. So I can now do my second level stacking model. I use a random forest. What this actually does, it doesn't only combine these 2 things, it can now actually combine them in a feature dependent manner. So sometimes in literature, that's actually called a gating model, gated stacked model. It's very complex, right? And that's this code here, okay? And you're completely free to define variants of this. We are not restricting you in any way. Just use your own creativity, implement whatever you want through this mechanism. And I guess the last thing I want to mention is branching. And branching allows you to control data flow in a complex graph. So for example, you might have some type of feature extraction, feature transformation, and you're not sure whether you should do A or B. So maybe you want to do either a PCA or an ICA to transform your features, so you can create a branch. So you can say data should either flow here and we do the PCA, or data should flow here and we do the ICA. And if you use this branch, you can use this PPL thing. So PPL is for partial pipeline, so a small graph, and this is basically an abbreviation. So you can construct this very quickly. And this gives you a computational element that has a switch parameter. So you have a control parameter. You can see this here, this control parameter branch, which you can set either to PCA to ICA. And if you set it to PCA, data will flow here. If you set it to ICA, data will flow here. Why is that interesting? One with PCA and one with ICA, 2 linear pipelines. Why do we need this complicated thing here? If you construct it like this, you will now have a hyperparameter that controls which preprocessing is executed, which means because it's a hyperparameter, you can have AutoML and hyperparameter tuning techniques figure it out automatically what works best. And you can have it figure it out automatically, even what works best with what learning algorithm and so on. So branching is actually a very nice mechanism to create complex AutoML systems from scratch in mlr3 pipelines. And I have a gallery post online that describes this in a bit more detail than I can do here in this. So most of this in this summary here I've already shown before. So we have abbreviations for certain patterns in pipelines. So this is this PPL thing. So this actually creates partial graphs. We haven't compiled many of these things, but we'll add more and more sugar elements. So you don't have to create like certain elements from scratch. So certain things that everyone always wants to use, we'll kind of store in the package. So you get these partial graphs and can directly work on them. So at the moment we have stuff, for example, for class balancing and chunking and then other stuff. And yeah, I guess I'll keep this now very short because I'm probably already a lot out of time. So I already said you can do a lot of nice things with mlr3 for AutoML. So you can kind of also see mlr3 pipelines as a design language to build AutoML systems. We are also ourselves very interested in doing that. So you can actually now create difficult structures and then have your hyperparameter optimizer figure out what works best. So very often you want to construct stuff like that. So different pre-processing methods with different hyperparameters, different machine learning algorithms with different hyperparameters, yeah, different feature extraction methods. So you can use branching, yeah, to kind of say either that or that or that. And all of these things have hyperparameters. And at the end, you get a kind of a joint space of all hyperparameters of this pipeline. And any tuner can now work on this. Yeah, so you can work with random search or grid search on this. But obviously, for these more complex things, you would probably want to use something more efficient like Bayesian optimization and so on to speed up the process in these high-dimensional tuning spaces. But from a conceptual point of view, it's not different than what I've shown to you before in tuning. And maybe let me directly go to the example here. So I guess hopefully that convinces you that you can do pretty cool stuff with this. So what I'm doing here is I'm basically writing down this. So there's also a nice plotting function for pipelines in the package. So I'm writing down something where I do either PCA for feature extraction or nothing. Okay, so I stay with the original features. Then I do a feature filter. I do ANOVA to filter down my potentially high dimension data structure. Then I do branching again, and I either use a support vector machine, I use gradient boosting, or use a random forest. And then I'm done. And in order to specify this pipeline for the complete thing, this is the code you have to write. Branching for PCA, your feature filter for ANOVA filtering, branching for the 3 learning algorithms with some IDs here that I manually define and some static variables that I define. And then these 3 partial graphs, I simply pipe together to my complete graph. I put it in the graph learner, and I'm now in mlr3, in the mlr3 world, and I can also use mlr3 tuning on this. And I specifically now want to use mlr3 tuning on this. So I can write down a very, very lengthy parameter set. I can say which feature extraction I want to use. I can tune the parameters of my ANOVA filter, of my random forest, of gradient boosting, of the support vector machine. I can add actually dependencies in there for hierarchical space. I can do feature parameter transformations. Okay, this is potentially a bit more complex, but this is very powerful. So if you kind of see these 2 slides together, they've kind of defined a pretty complex AutoML system already. And this is the hyperparameter tuning for everything, okay? So okay, that probably takes a few minutes to come up with this, but this is, it's 2 pages of code, and this does something pretty cool. You can fully parallelize this. You can do nested resampling on this, and you can change it as much as you want. And yeah, it's super definable and flexible.
We've seen that mlr3 pipelines can do a lot of things, and you can go full out and have like stacking and alternative path branching and so on. One of the first reasons why you would need pipelines, though, is pre-processing. And pre-processing you have to do when your data is in some way broken, or your learning algorithm cannot really work with it, and you need to adjust it to make it compatible with your data. So this is one step before you do pre-processing to actually enhance your features where you want to extract something. Here in this example I'm showing, we're working with data, but it's not really working with the machine learning algorithm we want to use. So this example you can also see online. So we, as you will probably also get the link, there's this page where everything, this is already rendered, and you can also follow the code. So what's happening here is that we are still using the German credit data that you've seen before, but in this code block that you don't really need to understand, everything that's happening here is that we're introducing missing values. So we're setting some of our data to NA. So if we look at our task now, so the task we have created, this has missing values now. I'm also going to initialize some seed in a resampling instance. So when we compare stuff, we get a fair comparison. So let's start with mlr3 pipelines. So we've seen the quite a few pipe operations, so pipe ops. Question is, which ones do we have? And we can just ask the mlr pipe ops dictionary, which is the dictionary that lists basically all of them. Or if we're in a hurry, we can also just write PO parentheses, because this one just prints us the dictionary. So let's start with this. We have a learning algorithm that we want to use, in this case, the ranger, random forest, and we want to train it on our task. But once we do this, we get an error message. So there's missing data, and our learner cannot handle this. So now we ask ourselves, what are we going to do? We can just impute. So we can ask our dictionary of possible operations that we have stored somewhere. Which ones of you can we use for imputation? And here it gives us a list. We can impute with a constant value, or with a mode, or out of range. You would have to look at these maybe if you want to make an educated decision. And the way you do this is that you ask your help. So you ask mlr pipe ops, and then imputist, for example. So in our studio, this opens a very nice browser help page, and this explains to us what it does, what are the parameters that we can set during construction, and everything we might want to know about it. So here we're using the out of range imputer. So this one we also get with this quick access function that Bernd already mentioned. So we just say, okay, pipe op, that is called impute out of range, or impute OOR. And this gives us a very nice object. So this is our pipe operation. It tells us some things about itself. So what its name is, what hyperparameters does it have, so what things are already set, and also the input and output. So this thing accepts a task and outputs a task, so it's a preprocessing operation. We can, this operation is, as Bernd already said, is basically a learning algorithm, like a generalized learning algorithm. So we can train this on data, and now we get the imputed data. So if we remember task $missings, we had some missing values. So this is the command that tells us if we have missing values in the task. If we ask the result of this operation here, well, I can just run this. This has no missing values anymore. So here the values were imputed. And so what does out of range do? Out of range for categorical parameters basically adds a new category that is out of range of the old categories. It adds a category missing. So before we had the credit history has a few levels, so factor feature, and here we had a missing value. Now it added the new feature missing. This is different from having a missing value, which the learner doesn't know what to do with. This is actually a new category, and that is called missing. And the random forest will have no problem working with that. We can now create a learner from this pipeline. So we can get this graph, which does first the imputation and then fits a learner. And this we again have to turn into a learner. So here we are in mlr3 pipelines country. We have a graph and we can add new operations to it, for example, but we want to use the mlr3 tools. So we want to go back to mlr3 country. So we create a new graph learner. So if we look at what this thing in here is, so hello. So this thing is a graph. It tells us, well, it consists of operations and they are connected in some ways. And but what we want is a learner. So this thing is a learner, and we can use it, for example, to train. And see, now we don't have any errors, and we have a fitted learner now, and we can even resample this thing. So this is going to, well, it has a certain performance. you can, I mean, we could also do benchmarks with this and, for example, see what different imputation methods work better or worse in this thing. And the nice thing is that you can use, as a more advanced feature, this branching thing that Ben showed, where we have the actual imputation of it that is being used as a hyperparameter. So we can make tuning over the method that does imputation. I'm going to skip the feature filtering. And I'm going to go straight to the robustification. So because it fits better into this narrative. So another way in which your learner can fail is that it is trained on features that are constant, for example, or that it tries to predict a feature that has, or that it tries to predict on a level that has not been seen before, on a factorial level. So I'm creating a task here that is a very small subset of the whole training task. So why am I doing this? It's a certain feature of this specific data that in the first few features, there are things that are constant. So for example, this feature, the first 30, no, not this one, but a few features of these, they're basically the same value for the first few rows. No, sorry, they are not constant, but the problem is the first few 30 rows, there are some features that occur in the task that are not seen in the first 30 rows. So what we're trying to do here is we're trying to predict a value that has not been seen before. So the random forest complains, the logistic regression complains. So I'm trying to predict on a feature that we haven't seen. So also, and now here we see the constant thing. Suppose we just have just 2 rows and we're trying to train a model on this one. Obviously this is destined to fail for various reasons, but one of the reasons is, well, we have some features that are not changing at all. So, and here we get the error message. There are some constant features, and logistic regression doesn't like that because it gives a well, zero determinant matrix. So what do we do in this case? What we can do here is we just collect all the different kind of operations we have that can fix the individual issues. So, and we because it makes the learner more robust, we call this robustify. So we say, okay, we might have a problem of missing of features that occur in the prediction side that we haven't seen during training, and the learner will fail. So we use the type of fixed factors, which removes features that we're not seeing during training and turns them into missing values. Next, we have to remove constant values, remove constant features. So there's a pipe up for that as well. It's like an iPhone advertising. For everything, you have a certain small tool that can do exactly what you want. And in the end, what we also have to do is we have to impute, because we had fixed factors remove some features, some values. Now we have missing values, so we also need to impute these. And here we have to be careful. We cannot impute out of range, because that would just be us introducing another set of missing values again, of unseen factor levels. So a feature I'm showing now is that, well, we have this graph. I printed a graph before already, but so this is the representation. It's not very convenient, so we don't really know what's happening. So we have a plot function, and the plot function, well, gives us a very nice representation. And here we have the linear graph this can obviously get much more scary, as you see in the slides from Bernd. You can have lots of different well, paths that go parallel and so on. A nicer way to represent this is to have HTML equals true, because this gives us an HTML representation. This is this is JavaScript doing some fancy things, and you can play around with it. It just looks nicer, and you can also zoom. So now we have this Robustify pipeline that does all these things. So it does fixed factors, remove constants, impute sample, and we feed this into logistic regression. So now we can train this on our completely broken task. I mean, this thing had like two rows and so on, but we can train on this now because all constant features were removed, and we can predict on it without trouble, even though we trained on a completely broken task that was had only two rows with constant features, but also the predicting task has lots of features, lots of values that were not seen before. Whether training on a data set with 2 rows gives you a good predictive performance is a different question. So, and now we've seen, well, you have to do quite a few things to get this, to get everything to work. Sorry about the noise here. So how nice would it be if, well, our package gave you a way to just build these things automatically and not having to remember what everything to do to make stuff robust. And here we actually have something. This is also what Bernd already showed, the partial pipelines. Here we have a few prepackaged solutions for problems that you might encounter. And one of these is obviously you want to make something robust. So, and how does this work? So we can just ask, okay, give us something to make stuff robust. And we get the pipelines, but this is a very big and complicated pipeline. Why is that? Because this thing tries to be ready for all the eventualities. So you say, well, maybe my learner cannot handle missing values, so I have to do imputation. Maybe my learner cannot handle factor values, so we have to encode to get numeric values, numeric features. Instead, we can also give this thing a few arguments. We can say, well, we give you this task we want to handle, we give you the learner that we have, and we run this, and this gives us a much smaller graph now. So it's not this huge anymore. It's just noticing, well, the few things it actually has to do. So it doesn't need to encode stuff anymore because our learner can handle factorial features. Instead, it only does the necessary things. And this one, we can also train into prediction, and it learns the same way it did before.